Okay, so good afternoon, everyone. So first, really happy to be here to share some of our recent work. And today, I'm going to specifically share some of the work we did for, those methods which is slightly different than the classic image prior for image restoration. And specifically, we're using deep reinforcement learning and, joint modeling and disentangling for image restoration. Right. Oops. It doesn't work. Okay, good. All right, so we have already got 3 afternoon talking about image restoration. So I'm really working in a similar field where we really want to kind of have a good method and model to recovering the image from different sensing modalities, like people talking about MRI, people talking about CT, and image restoration. So basically, we are trying to sense the real world, like analog signal, to get some digital measurements. And again, we want to reconstruct the analog images with the high quality. And the question is, how can we come up with an effective method to do that? And this is really the fundamental question like we're all working on. And and in fact, many of the image restoration problems is in fact a linear inverse problem. And for those of you who are familiar with that, and they can be actually generalized using the, a very simple linear equation, like y equal to ax plus e, where your y is your whatever measurements you have in different domains, and you want to recover the x as good as possible. So this includes many inverse problems. The most fundamental one probably is the image denoising. You want to, recover your underlying images from your noisy measurements, right? And also, many of you are now using smartphone, and probably there's a module called super resolution in there, which will try to recover the high resolution images from low resolution measurements. And this is also another example of inverse problem. And just now, many speakers mentioned about MRI, right? MRI is also a very perfect example for solving an ill-posed inverse problem where where the measurement is no longer in the image domain, but in the k-space. If you do undersampling, you are having a undersample k-space measurement, and you want to still recover maybe the images of your brain or maybe other parts of the images. And then the question is like, what is the the key ingredient or factors to come up with a good solver for for all of these inverse problems? In fact, many of the problems we're actually solving this. Fundamental MAP problems where you want to minimize the fidelity term together with the regularizer that you develop for your images, right? So here the Y stands for the measurements, A is your sensing matrix, X is the signals you try to recover, right? And in fact, what we're working on is really the second term, right? The regularizer. And we are trying to work on different data models priors to construct such kind of regularizer. Maybe some of them are based on the well-known image priors. Some of them are data-driven. We're using learning to come up with a data adaptive kind of models. Some of them are based on the specific structure of the signals, right? So fundamentally, what the role of this data model is to differentiate or to trying to figure out what is the images, right, you want to recover from something else. Right, if it's denoising, you are trying to differentiate images from noise. If it's like MRI, you are trying to differentiate images from different, aliasings, artifacts. And this is really fundamental role of data model, right? And and then if you take image denoising as an example, right, what we are normally doing is really in the following form, where you're trying to kind of analyze or project your noisy images into some latent space, which we call that encoding, and you impose certain structures in this latent space. And then after imposing these structures, you're trying to recover the images. And hopefully, this recovery will be better, will be more like the underlying clean image. And what kind of structure you want to impose in this latent space, right? There are really many models, methods people have developed. Maybe the most popular example is the sparsity, where in this case, Z well stands for the sparse codes in either the dictionary domains or transform domains. And people have worked on this for many years. Like you can trace back to the signal processing approaches where people use DCT, use wavelets to come up with a sparse representation for image compressions, for different applications. And more recently, people working on dictionary learnings, synthesis dictionary, analysis dictionary, which people trying to learn a better representation or models for certain images or certain data, such that the sparsity becomes even better, right? And actually, I myself and Sai and our PhD advisor, Yuan Brester, we work on not learning dictionary, but learning transform, which is another way around, which we can not using the predefined transform, but we learn one from. And hopefully, this one give us a sparsity and eventually better denoising results, right? So not only sparsity, like I think yesterday, many speakers like Prof. Ima and other Qing talk about like no matter whether this is sparsity or low rank, this is nothing but a low dimensional representation of the data, right? That's what we want. So also there are many people working on not really projection onto a union of subspace. They're just finding a subspace for low dimensional representation. Also, we can use this for denoising as well on top of sparsity. And by having this a success of dictionary learning, analysis dictionary, synthesis dictionary, it shows that it is kind of true that using data-driven approach, like a learning-based method, can give you a more effective, data representation or model comparing to those analytical models, such as like, we use TV, we use sparsity with X transforms, and they turns out to be more effective, right? So following this line, now the trend is more like say, hey, we don't want to use maybe a simple transform or dictionary. We go for even deeper structures. We come up with a deep neural network, and that is the one we use as the encoder here, and such that now your latent space representation becomes a deep feature embedding, right? You kind of make your embedding or encoding process more flexible. You allow like much richer structures instead of just a single layer transform, right? And we see some of the successful works, and some of them also mentioned by the previous speaker, like those one used for denoising, super resolution, and they show much better results or effective results for lots of applications, right? Okay, so no matter what kind of model we are using, right? What we are doing actually, we are trying to say restore the noisy images to the clean image estimation using all sorts of structures like sparsity, low rank, or even deep prior-based low dimensional. Right. So all of this, I mean, most of the works we have seen so far are focusing on how to model the images in the effective way, in the accurate way. But actually, the question like we are, thinking recently or we're trying to argue is that, well, we kind of overlook the other part, right? So besides the image we're trying to recover, there's also one part we removed, which is the noise, the corruption. So what about the model for that noise we remove, right? Is there any kind of constraint or penalty or regularizer to say something about the part that we remove that we kind of don't want eventually? Because that part also have some structures or have some distributions, right? We should say something about that, right? So this is actually some of the kind of the questions we're kind of investigating. And I can show you some example, right? So for example, this actually DNCN is, well, it may not be the state of the art, but it's one of the popular deep denoising network people use for restore noisy images, and they can actually recover images from like noisy measurement and get a pretty good reconstruction results, right? But if we look at the residual, definitely it's not perfect. There's still some, modeling errors or residuals after reconstruction. But if we look at the noise map or the residual amplitude, we still see some structures. I mean, you can clearly identify the correlation of this residual and images, right? This is not a good sign because those correlated structure may corresponding to the true images that you accidentally removed. And those are the sources give you the over-smoothing or artifact. And we really don't want this. And our kind of argument is that, well, it's because we didn't impose any laws on these parts such that they accidentally remove the true images, which is something you want to kind of avoid eventually. So that one gives our, pose a question to us like, well, we would like to argue, well, sometimes even though we have so many good deep image prior data structures, it may not be good enough to only set constraints or penalties on X, right? So how about we should add noise modeling as well in the loss or objective function explicitly on top of the image regularizer? Or maybe if it's not denoising problem, it's other image restoration problem, can we jointly modeling the corruption model as well? Suppose that the model itself is not accurate. I think just now, Prof. Reinhardt, they also mentioned about distribution shift and also a forward model inaccuracy in practice. So this one kind of triggers some problems for jointly refining the forward model together with the image restoration. So this is the first kind of question or problem we are trying to investigate. I'm going to share some of the results we have. Another kind of problem we are thinking is that, well, instead of solving the whole restoration problem in one step, right? Sometimes this is hard, especially if you have highly yield-post problem. Solving directly as a one-to-one mapping may not be robust or accurate enough. So instead, how about we solve this problem in a progressive way, right? Don't have to be one step. We can do this in multiple steps, such that we would like to argue that, well, deep reinforcement learning is a good tool for like some of the challenging image restoration problems. So later we're going to share some examples to demonstrate that there's some promise on this direction as well. Okay, so let's look at the first question, right? We would like to share something about, say, joint image and noise or degradation model modeling. Okay, so I used the same example just now, right? Just now we're saying that, well, even though we have a really good model, image model, say learn deep priors or other models, most of them are just for images, right? Sparsity is low rank as well. And I think yesterday, I attended, Prof. Ma's talk. He also mentioned that, well, in fact, there's no exact model for images, or there's no perfect model for images. All of these things like sparsity, low rank, they are approximate models, right? It's like some assumptions we make for images, right? And because these are not perfect models, there's always modeling error, which will contribute to a reconstruction error or residuals. These are something we call that remaining noise or modeling errors, and we trying to avoid, like we don't want to see this kind of highly correlated residual that is to the images, and we try to avoid that. We try to minimize those kind of structure patterns in the residual map, right? Okay, so what we're trying to propose here is, instead of having a regression type of problem from noisy to clean images, we should maybe trying to reconstruct it jointly the images and the noise. Right. So what we're trying to propose is that, well, instead of just mapping from noise image to clean image, maybe we should jointly reconstruct, say, noise image as well as noise image to noise. Right. So then you have two layers or two record rights jointly apply to this reconstruction process. Right. So in terms of formulation, conventionally we're looking at some denoising problems where we minimize the loss function, which is completely build up or design based on the image prior, right? But instead, if we're talking about joint modeling, right, our objective function should have two parts. Like one part is mainly for images, the other part is based on our prior knowledge or assumptions on the noise or the corruption themselves. So jointly, we believe that the learn parameters can perform a better job for image restoration. Okay, so in fact, there are many choices of the so-called encoding process or decoder we are going to have, but our preliminary work, we choose this specific method called neural flow as the encoder. The reason is that this neural flow method gives us some good property as so-called invertible linear transformation. The reason is that, well, we want to jointly recover both, so we want to make sure that the whole encoding process is lossless, meaning that you're not just removing things, you want to keep the things you remove as well. So neural flow is kind of the good candidate we choose as the encoding process we use in this preliminary work. And in fact, what we're doing here is in the training stage, we're trying to encode both the noise images and the clean images jointly, and we're trying to set up loss function and the objective function for every part of them, like reconstructed noise, reconstructed images, and also we also swap the noise features between the two branches and trying to come up with some adversarial loss between the noise images and clean images, right? So eventually you will have some kind of hybrid loss to model them jointly. And for the noise, this part will depend on the noise you have. This is one example. Suppose we know the noise is IID Gaussian, but in fact it may not be IID Gaussian. If it's real noise, probably you are going to change the noise, the loss term for the noise, right? Maybe it's just independent, not necessarily the IID, right, in this case. But in the training stage, we have a hybrid loss, but in the testing stage, the denoising step, it will be super easy, right? So what you have to do is, once you have this training encoder, you just need to encode the noise image using your encoder, and then you just zero or maybe randomly replace the noise factors with the small perturbation, right? And after that, you use exactly the inverse flow to reconstruct the images. And interestingly, we find that, well, if you think about the whole pipeline, right? If you replaced here the flow, which is a deep network, let's say we do not learn it. We use the conventional DCT and wavelet as the transform. The whole process is exactly like the very familiar with transform-based shrinkage method, right? What you're doing here is you transform the images into your transform domain and you're trying to recover it, right? But the only difference here is that we're replacing the transform with something more complicated, right? But still, the nature is the same. We're trying to find some kind of compact and sparse representation in the latent space for denoising eventually, right? Okay, so, but then the question is, does it work? Well, we have some preliminary results, right? This is actually the result I just showed you, like without any modeling of the noise, just by training, say, a DNCN for, like, as an image prior. And we end up with some, really structured noise or residual map. After the noise modeling, I mean, jointly with the previous image modeling, we kind of, well, still you will see some structure there, but kind of more random than the previous noise map. And you can see that, well, the PSR also increased a little bit. I think approximately 0.5 to 1 dB comparing to the, the conventional regression-based methods. And more importantly, if you compare the restore images like side by side, you will see that, well, this method, our method by joint modeling, they will preserve more high-frequency components, right? You kind of get rid of those over-smoothing artifacts, which are pretty common for, like, say, a regression-based deep learning methods, right? So visual quality, from the visual quality perspective, we think this is quite effective. And we also do a lot of testing, and this is actually quite similar to the talk given by, Prof. Ringha just now, right? Where we're thinking about, robustness or generalization in practice, right? Because in practice, we cannot guarantee that the sigma or the noise level in the training will be always matched with the testing, right? It's possible that you get some images which is even noisier than your training images. And we find that this is a common challenging for existing, denoising methods because, for example, here, if we set the training sigma, the noise level to be 15, you will see that if the testing sigma somehow deviate from the training sigma, you get the performance drops quite significantly, right? And we want to avoid that. We want to good denoising results by making the method more robust, right, or more generalizable. And it seems like this joint modeling idea is a good candidate for such kind of a robustness results. And I show another plot. This is also very similar to, Prof. Ringha just now, he showed, right? So as your testing time distribution or the noise level gradually deviates from your training time, right, you will see that other method, the performance really drops, and you will see a larger gap in terms of the denoising results or quality, whereas having this joint modeling, the final one, I mean, of course, it still drops, right, because your noise level increases, but the degradation is actually less severe, right? It's kind of better than doing just image modeling. So we think this is a good approach to trying to improve the generalization and the robustness for denoising in practice. Right, and also we also try something like, say, non-uniform noise, which is another type of, robustness. Like we're assuming that the noise itself is not uniform, right? So if you train using 1 sigma, you are talking about handling spatially varying noise in the practice, in testing time, right? And we also try like real noise. In this case, you have no idea about the noise distribution at all, and they can be hybrid, they can be non-uniform. And we show that, well, having a joint model will make the whole model more restrictive. And so also it can prevent some kind of overfitting in the training time, right? So this is the first work. And also, by the way, because we are explicitly reconstructing the noise, so we find that this is also a good approach to learn the real noise distribution, right? So in principle, well, by having this joint reconstruction, we can not only reconstruct the images, we can also try to reconstruct the noise. So give us a way to kind of learn what is the distribution of the real noise, right? If you give me some samples, I can try to have some kind of generative model for noise as well. So in fact, we have ongoing works on this aspect, but since we don't have good results, I don't show them, but this is perfectly possible, right? Okay, and then another example is that, well, just now I showed like a super simple example like Gaussian denoising, right? But, just now Prof. Rene also showed this kind of adversarial examples, which to my opinion, it's a special version of denoising, right? I mean, if you look at the adversarial perturbation, beta here is also an additive components, but the only difference here is beta itself is not random. It's a highly structured one. You train specifically for fooling the classifier, right? But, if we want to remove it, right, this is some kind of a denoising problem, which we call that purification, right? You are trying to reconstruct the normal example from the adversarial example, right? And also, this seems like this is also another example of inverse problem. And because it's an inverse problem, we need to have some form of data prior or image prior. And we find that, well, many of the so-called purification methods really similar to image denoising. They have CAN for regression. But we would like to argue that because this perturbation is so structured, you need a separate model for the perturbation as well, right? So this one gives us the idea, like we use the similar kind of idea to not just directly reconstruct the images, but we're trying to disentangle the images from the perturbation. And we set up loss function for the perturbation and separately, right? So it's some kind of joint modeling of the images and also the reversal perturbation. And by doing so, we show that it works pretty well for, like just now Prof. Renee mentioned that there are many types of attacks. So we try some of the popular attacks we know, and it works reasonably well comparing to other methods. And also, we also try different, like a vary budget, right? Sometimes the attack is kind of stronger, sometimes it's weaker. And for different kind of budget, the method can always, like most likely try to remove those perturbations from the adversarial samples, right? And this is kind of contributed by having this additional regularizer and loss function for the perturbation themselves. Okay. So, I don't know why it's like that. Okay, so just now I show like two examples which are most likely denoising, right? Even if one is random noise, the other one is structured noise. But this kind of idea can also apply to something more complicated, right? Some other little bit more complicated inverse problems. For example, like we have been investigating this, shadow removal problem, which is something like take a photo, maybe under the sunshine, and probably you have some shadows because certain object may block the sun, right? So we want to enhance the visibility of the shadow region by maintaining the quality of the whole images. So we need some kind of algorithm to try to recover the underlying, high visible images from the shadow version, right? So conventionally, people just treat this input as shadow region plus non-shadow regions. But we are thinking, well, the model can be more kind of sophisticated than the simple combination, right? So we trace back to the physics of Retinex model, where they model the measurements as the multiplication of reflectance and the illumination, right? And we think that, well, for shadow case, the only difference is that the illumination will be inconsistent across shadow and non-shadow region. But the underlying reflectance is actually the same, right? They are just the normal natural objects we have in practice, right? So we use this to kind of have a more, rigorous formulation of the shadow removal process. And by having, well, both the regularizer for the underlying reflectance, here the reflectance is a little bit like the X we have, like the underlying images, as well as the consistency of the illumination, which is something like your degradation model. By having the joint modeling for both, we show that the whole process can make some of the existing deep learning network more effective and efficient, right? So we pick one of the one of the recent progress in VIT, right, vision transformer, which are demonstrate usefulness for many low-level vision problems. We try this for shadow removal, but as actually just now the speaker mentioned that the transformer, one of the issues is that their efficiency is not that good because in terms of the model complexity is really much higher, normal CAN, right? But we think that the reason is because they have a self-attention mechanism where they're trying to construct the correlation matrix throughout the whole feature is expensive and takes a lot of time, right? But we argue that for some of the problem like shadow removal, you don't have to calculate the correlation matrix through the whole image. Instead, here what we really care about is really the consistency between the shadow and non-shadow region, right? That's really the key we want to impose in this process. So because of that, we kind of change the very redundant global self-correlation calculation to a specific correlation matrix, which is only between the shadow and non-shadow region. We call that shadow and non-shadow interaction. And turns out that by having this more careful modeling of the degradation process, we can end up with a model that has much fewer parameters than the existing one. Right? You can see that actually the model size may just drop like more than 10 times than the previous state of the art. And provided that we also have better performance, right? Our shadow removal PSR and SSIM can also improve comparing to the existing state of the art, right? So this is kind of owned by, have a understanding and modeling of the degradation model as well, right? So, I mean, in terms of the numerical things, we think we achieve a much fewer number of parameters and with more promising results in the shadow removal. And this is also have the idea of having a more effective use of those limited parameters by having better understanding of the degradation process for a particular task, right? Not a generic model, but a very task-specific deep model in this case. Okay, and you can see some of the results, like existing models, usually they still have some artifacts, even after the shadow has been removed, you can still tell the boundary artifacts, whereas if we purposely impose the shadow and non-shadow interaction, those boundary artifacts can be alleviated in a much better sense. Okay, so this is actually some of the recent works, and actually after this work, right, actually my student, he also tried very similar idea with diffusion model. I think just now also many people mentioned about diffusion model, which is also quite popular. And surprisingly, it doesn't work very well. You see, this is actually the diffusion model my student trying to generate. He's trying to train a generative process of shadow-free images using the shadow mask given by the data set. And we find that, well, you can always see some kind of artifacts there. And we find that the problem is actually because the mask estimation was wrong at the first place. Right. Because this mask estimation is normally by human annotation, by some algorithms. And it's possible that we end up with inaccurate mask for shadow modeling. So that give us the idea that, well, not only trying to remove the shadow, we should jointly also trying to refine the shadow mask. Because no one can guarantee that this mask is accurate, right? You have to assume that there's some inaccuracy in the mask estimation in the first place, right? So we kind of modify the original idea of training a generative model for the shadow-free image alone, but together we're going to combine the degradation prior also into this diffusion model. In this case, we're trying to jointly refine the mask with the shadow removal process, right? So this one gives us some kind of idea to come up with an unrolled network, which is based on the existing understanding of the shadow model, like the retina-based shadow model, together with a joint model, like a DMDM for not only the images, but also the mask. So in the whole generation process, the images will be kind of gradually generated from the random noise, and together, your mask, which initially is not accurate, will also be gradually refined to achieve a better kind of estimation, which doesn't really prevent you to recover the shadow regions in the end, right? So having this joint modeling, okay, I skip those details because, in fact, we have a rigorous formulation. We're not designing this as some, assembly of networks. Everything is actually an unrolled network based on the, standard MAP problems we have talked about in the first place. But in the end, I want to mention that, well, having this joint estimation of the mask and images will give us even better results, and just considering the image restoration process. And this is by considering the correlation between the mask and the images, because these two are not independent. These two are kind of highly correlated in terms of their shape, their kind of regions, and you can use each other to refine the other part in the actual shadow removal process, right? Okay, and I show some examples where you see this is one perfect example that in practice the shadow is actually here and also the bottom right regions, but the estimated mask doesn't really reflect that, and that is the reason like most of the images, most of the method, they didn't capture the shadows on the right, right? But by jointly estimating the mask, this part can also be removed successfully by the joint modeling. And another interesting thing is that if we can have a joint refinement method, we don't need a very sophisticated mask estimation, right? We actually try that user can just do some sketch. They just give us some idea about where the shadow is, and the whole network will automatically refine it to something much better, right? Get rid of maybe the expensive process of mask estimation as well by jointly considering the image prior, right? Okay. All right, so this is my first part. I want to summarize the lesson we learned through all of this practice, right? So we would like to argue that, well, sometimes it is limited for restoration to only rely on image modeling, even though we have lots of good tools for image prior, image modeling. And we would like to argue that for image restoration in practice, maybe a better idea is to have a joint image and degradation modeling for reconstruction. If you know something about your degradation, your noise, your forward model, and if you have the feeling that your degradation is inaccurate, it's better to have a joint modeling method than just image prior. And we show some of the results showing that having a more accurate joint modeling will eventually lead to a better image reconstruction in practice. Yeah, this is like some of the takeaway message we have for the first part of my talk. Okay. And also I want to share some of the work we did, which we tried to argue for hard image restoration problems, solving them in one step may not be a good idea, right? Sometimes if we solve the whole problem in a progressive way, it may give us some good merits in terms of robustness, in terms of generalization. So let's show work we did. We start with the same example. Just now we mentioned about shadow removal, right? So if we make it more general, this is about enhance the low light images, right? Shadow removal is just like enhance the lightment of the shadow region. But if you make it more general, it's about give me your low light images, I can enhance them towards a better visibility, right? And it's still following this Retinex model where you're trying to restore the images from the low illuminations and to some normal illumination. And simultaneously, you want to remove the noise, and also you want to estimate the so-called optimal illumination, I optimal here, right? But actually, the question here is, nobody knows what is optimal illumination. Like say denoising, where there's a clear definition of underlying clean images. So-called optimal illumination is really subjective, right? So I can give you some example, like most of the low light enhancement method trying to learn the one-to-one translation from the low light images to some enhanced, or normal light images, right? By using some networks or maybe using some conventional signal processing methods. But in fact, we think this deterministic one-to-one translation have some limitations in practice. For example, if you give me a data set, right, training data set, it's very likely that both the illuminations, the so-called low illumination and the optimal illumination may vary from sample to or by using individual subjective evaluation. I mean, your evaluation metric is different, the so-called optimal illumination may also be different. Right? And not mentioning that the degradation process may not be consistent among your training data, right? Because some training data, the low illumination images may be like much darker than the other ones. So you don't have like a consistent degradations in the training data. Having this kind of observations, we propose to not do this in one step. The idea to do that is to use something like a reinforcement learning to do this restoration progressively and treat everything as a Markov decision process, right? So visually, what we're talking about is that, well, giving you a bunch of low light images will allow them to vary from sample to sample, some of them brighter, some of them darker. And when you do the enhancement, we also allow the user to customize which enhancement you like, right? Sometimes you want to make it darker, sometimes you want to make it brighter. It's really up to the user to do it. We offer multiple copies by adjusting the number of stages where you use for your agent, your trained agent in your restoration process. Okay. So I think here the key is that we're trying to model the whole low light image enhancement as a Markov decision process rather than a deterministic one-to-one mapping, and using a deep reinforcement learning. And here the state referring to the low light images, but not necessarily the initial images. They can be intermediate images, like after we're running this agent for several times, right? And also the action here, we're using those parametric light adjustment AT, which we're going to talk about later. In this case, it will be light adjustment curve that we parameterize the whole curve definitions and allow those parameters to be learned, right? And also, by having these definitions, the whole low light enhancement process can be modeled as an MDP trajectory from your initial state, action items, and then followed by the next state, right? So by forming these MDP trajectories, you can set up some reward function which is linked to your quality of evaluation. You can use PSNR if you like. And later I'm going to show you that we follow something like a non-reference because we want to achieve some kind of zero-shot image enhancement. But of course, this reward function really depends on the quality assessment as well, right? And now your agent will become some kind of policy network, which you can try to learn with the trainable parameter theta, and it's going to map the current state to some probability density function over the actions eventually, right? So like I said, in our case, I mean, this is really task specific, right? But for light enhancement, our action will be used to characterize a second order light enhancement curve. And by using this LE multiple times as MDP, we can try to approximate even higher order light enhancement curve as well. So I'll give you one example. Eventually, after multiple iterations, we're talking about the actions going to approximate some kind of a pixel value adjustment in the between the low light images and high light images. And the learned action eventually will form some curve within these boundaries. And hopefully this one will try to map from a collection of low light images to some normal light images according to customer's subjective metric, right? So eventually the network will look like this. And like I said, the loss function, the reward function we choose, we didn't follow the standard, let's say, mean square errors or SSIM. Instead, we're following a paper like previously called Zero DCE. They're using a completely non-reference quality metric, such as like age enhancement, light, like channel balance, all of these, which are demonstrated quite useful for like light enhancement applications. So I can show you like one example. By having this customized progressive image enhancement process, in fact, the result you have is, it depends on how many stages you have, right? You can progressively enhance the light from the input images and eventually, 4 times, 5 times, 6 times, and gradually increase the light. And the user can actually choose which, version they want, right? According to their quality evaluation. Okay, and if you plot the PSNR as a function of number of steps, of course, there will be some kind of a peak value, which is exactly matched with your training number of n. But even though if you run more times or less time, the PSNR drops, but sometimes the visual quality may be better, right? So it's really subjective to the quality evaluation you have eventually at the user end, right? Okay, I'll show you some visual example where having this, reinforcement learning method can generate some of the better visual quality than other existing methods. And more importantly, because this kind of deep reinforcement method is something like a recurrent neural networks, the number of trainable parameters is much fewer than many of the existing methods, such that we can actually achieve something like a zero-shot learning, meaning that you just give me one images, the testing images are only in training on that simple testing images, and try to recover an agent that is working for that test image. Something like a testing time training, but make it more extreme, right? But you can only achieve this by significantly reduce your model complexity eventually. Otherwise, you are stuck into some overfitting problems in practice. Okay, so we also do some other, practice, not only in enlightenment, but also maybe denoising. I will skip some details, but basically, for different applications, right, the only difference is the action you are going to use. For enlightenment, the action may be the curve. For denoising, the action will be the residual values from the current stage towards the clean image, right? And again, we're treating everything as a MDP trajectory for denoising. And we also show that, well, theoretically, the whole like deep reinforcement learning method eventually end up with something similar to RNN, right? But only difference here is the way you train them is quite different. And because the way you train them is different, they kind of provide some kind of a stochastic version of RNN and end up with various merits such as robustness, later I'm going to show you, in denoising in practice, right? So this is also very similar to the robustness I just mentioned, right? We're assuming that our training noise level is certain, like say 25, but the testing time sigma or the noise level can vary. Maybe sometimes they're higher, sometimes they're lower. And this one will bring some problems for some of the existing denoising method, like say DNCNN or FFD-NET, right? But in practice, having this reinforcement learning-based method will demonstrate better robustness comparing to the so-called regression-based method owing to the way of training, right? And also, we try another sigma level. We have something similar conclusion as the previous one. And we also try this for real noise removal, where I mean, we have some images and we have no idea about the noise structures. They may be hybrid noise, they may be non-uniform noise, and we try different methods to, to kind of try to remove the noise as much as we can. And we show that the robustness will also be very useful for dealing with real noise. Right? Okay. And just some recent work actually I did with Sai. We have collaboration on this, plug and play method together with a deep reinforcement-based denoiser, and we can extend the usefulness to maybe not only denoising, but other inverse problem, right? So we also try like a deblurring or super resolution, and also here the problem is the observation model may not be inaccurate, right? So there may be some kind of shift from training to testing, and how can we deal with those robustness issues in practice? That's like a challenge. We think reinforcement learning method will have some unique merits on that because they end up with lighter weight deep models and be more robust to address to those drift in the observation model in this case, right? So the idea is very simple, like we are trying to change the denoising process with a plug and play formulations, and we have some iterations through data consistent step and also incorporate those pre-trained DRL-based denoising. And we see that, well, given the shift in the forward model, right? For example, in this deblurring process, if our training kernel is like 2.0, but our testing blur kernel is something different, right? We observe some degradation of, some competing methods, but we see some reasonable robustness by having a DIL-based denoiser compared to other methods. And similarly for super resolution as well, you may have some deviation of the kernel as well, the blurry kernel. And we see that this kind of robustness will be a good kind of merits brought by this DIL-based denoiser. Right? Okay, so just want to summarize by the lesson we learned from the second part. We see that, well, some regression problem, instead of treating them as a one-to-one mapping, it may be modeled as an MDP as well. And by dividing the, the very relatively more complicated restoration into multiple stages, it's possible to make the challenging problem much simpler, right? For example, we can decompose the light enhancement into multiple stage curve enhancement, and maybe we can decompose the denoising problem into some residual estimation problem instead, right? And also, we observe in practice there are some, these kind of methods leads to better generalization and robustness. And also, by having a lighter weight network, sometimes it can enable, a zero-shot learning or unsupervised learning, rather than, supervised learning over a very large data set. So these are some of the merits we observe for this kind of trial and methods. And for that, well, and the last but not least, we think this is a kind of approach, something like a divide and conquer. So it's a better way or smarter way to tackle challenges in practice. So you don't have to solve everything in one step. You can try to solve them in a progressive way in this case. So by having that will conclude my talk. And thank you, and I'm open for questions.
Well, maybe I can start. So for the first part on disentangling, I was wondering, have you thought about, connections between what you're doing for disentangling signal and noise and sort of a more information theoretic perspective on it? Because I was reminded of, things that people have done in privacy aware,
yes,
deep learning, there's disentangling and stuff, right? So what connections do you see?
Yeah, I mean, that's a really good question. In fact, we have some ongoing works looking about that problem. For example, you just mentioned about the privacy issue, right? Some of the work we mentioned, like adversarial purification. We also study like what is the kind of the how to say, like say correlations or mutual inference between those adversarial perturbation and images, such that if we have such kind of theoretic guidance, it can give us a better idea to impose especially those laws to try to differentiate the images from the perturbations. Right now, all of this loss design is still based on some kind of assumptions and priors. There's no, how to say, theoretic, kind of guidance for it. We're now working on some of the results. For example, we did some kind of a set theory analysis on adversarial perturbation, but since it's not published, so I didn't share with that. And also regarding the second part, the reinforcement learning, right? In terms of robustness, we're also trying to work on some of the robustness guarantee, maybe as a function of number of stages. I guess if we can get it, hopefully I can share maybe in the next workshop, hopefully within a year, yes.
Thank you. Maybe I can ask one more
sure.
question then. So, or maybe it's more a thought.
Sure.
So you were talking about doing the image reconstruction or restoration sequentially, and you also had, a work with the diffusion models, which are also have the sequential process. And traditional iterative reconstruction is also has an iterative process, different from like just a single shot applying a neural network to recover an image. So maybe a thought is like, is there a way to unify these iterative methods, whether involving a neural network or diffusion or not, into a more common kind of framework, right? So that was my thought. Like, what are your thoughts on that?
Yes, I think that's also a very interesting question. In fact, we talk about that in the diffusion paper we put in the archive. In fact, you're right. If you look at the diffusion model, right, the way they generate the images from the, say, random noise is also like in a progressive way. I think that's a really a unique advantage because, for example, the work we're doing here, we're having an unrolled network where you also need to progressively doing this kind of projection onto your, I don't know, your data consistency term or your fidelity term, right? And if we're not using diffusion model, maybe we're using, say, GAN-based method, you have to run the GAN-based method multiple times, which increase the complexity and make it more expensive. But diffusion model is good because itself, it's a progressive method. So then we use it for unrolling network. It doesn't really kind of cost additional time because if you have anyway, you have to run this progressive diffusion model progressive time. So the only additional cost is some kind of back projection. You just need to impose additionally this data consistent term. So I think that's a kind of a a good match with many of the iterative methods like unrolling and plug and play. I think I totally agree with you. I think it's kind of they have the similar nature, so seems like they are a good match between the two, right? Yeah.
Okay, so if we don't have any further questions, let's thank Bihan for
thank you.
his wonderful talk.